Now that you know all the matrix operations, we're going to go back and talk again about matrix characteristics like dimensions and size. It's going to give you a new outlook on it. Okay, first of all, this is kind of review, but the dimensions of a matrix are expressed by saying the number of rows times the number of columns, and the number of rows always comes first, okay? So the rows are in this direction, right? And the columns are going to be in this direction, all right? And the number of elements you calculate basically by multiplying the rows times the columns, right? So if you have 2 times 3, the number of elements is going to be 6. The other way you could do it is you could just count up the number of elements, from the beginning to the end, right? So like this is a 2 by 3 matrix, 2 rows, 3 columns, and I could find out the number of elements simply by counting them up to 6. Okay? All right, moving on. What is a row matrix? What is a column matrix? What is a square matrix? Well, like we said at the beginning, a matrix is like a rectangular table of numbers. And a rectangle can be a square, right? So one of the possible matrices is a square matrix. A square matrix is just how it sounds. You're going to have the same number of rows as you have columns. So this, for example, would be a square matrix. You could have a square matrix that is also 3 by 3, right? Or 4 by 4, or 5 by 5, or even 1 by 1. That's also a square matrix, okay? So that's a square matrix. So what's a row matrix or a column matrix? A row matrix and a column matrix are kind of how they sound. So a row matrix is basically a matrix that is composed of one row, okay? So that's a row matrix. A column matrix is a matrix which is composed of one column, okay? So row matrices, column matrix, and square matrix are just special sizes of matrices, and they have their own special names. Now we're going to talk about a specific kind of square matrix. This square matrix has the following characteristic. In the top left corner, he has a 1. And in the bottom right corner, there's a 1. And every other element in the matrix that is along this diagonal, there is a 1. In every other position, there's a 0. So this has a very characteristic format, right? It's got 1s down the diagonal, and they call that the diagonal, of course, and then the other elements are all 0s. This is called an identity matrix. The reason why it's called an identity matrix is if you multiply this matrix times a matrix that is compatible in size, you will end up with the exact same matrix you started out with. Okay? So let me show you how that works. So if I multiply this matrix, now I'm going to do a 2 by 2 because it's a little easier to do the calculation, okay? So I'm going to multiply this 2 by 2 matrix times another matrix, and the other matrix I'm going to multiply it times is this blue matrix here, okay? And remember that when we are going to multiply two matrices together, one of the easy ways to do it is if we position the first matrix to the left and the second matrix to the right of the answer matrix. So we're going to put the answer matrix here, and we're going to say, okay, first thing I'm going to do is I'm going to multiply this row times this column, and I'm going to multiply the corresponding elements, 2 times 1 and 0 times 4, and I'm going to add those together. That gives me 2, right? And then I'm going to do the same thing with 1, 0 times 3, 5. So 1, 0, 3, 3, 5 is going to give me 3 times 1 plus 0, which is 3. Okay? And then I'm going to do the same thing on the bottom row. So I'm going to have 0, 1 times 2, 4. And I'm multiplying the corresponding elements. 0 times 2 plus 1 times 4, it's going to give me 4. And then finally, I'm going to do 0, 1, and 3, 5. So 0, 1, 3, 5 is going to be 0 times 3 plus 5 times 1, which is going to give me 5. And then you notice that my answer matrix is the exact same matrix as the blue matrix. So if I multiply the identity matrix, which is basically 1s down the diagonal, 0s everywhere else, if I multiply the identity matrix times another matrix, the other matrix is going to be the answer. And so basically it's kind of like when you say 1 times 3 is 3, 1 times 50 is 50. It's like when you multiply 1 times something, you just get the same thing back. And that's the same thing that happens when you have the identity matrix. It's kind of like multiplying by 1. And that works in both directions. So if I do 1, 0, 0, 1 times matrix 2, 3, 4, 5, I'm going to get the same thing back. And if I do it in the opposite order, it's also going to give me the same thing back. And actually, matrix multiplication usually does not give you the same result if you change the order. But in the case of the identity matrix, it doesn't matter the order, because if you multiply the identity matrix times anything, whether the identity matrix be first or second in the multiplication, you're always going to get the same thing back as the other matrix. Okay? So the answers to both of these are going to be the other matrix that's not the identity matrix. Okay. Last of all, I'd like to talk to you about the zero matrix. The zero matrix would be any matrix that is composed only of zeros. And you can have any size of zero matrix. But one of the sizes of zero matrix that's most popular is the square zero matrix. And the reason why is it's kind of like the identity matrix in that the result from the zero matrix multiplication is very predictable. Whenever you take the zero matrix and multiply it times any matrix, guess what you get? Yes, a zero matrix. Okay, so zero matrices are like multiplying by 0. 0 times 7 is 0. 0 times 8 is 0. 0 times anything is 0. The zero matrix times another matrix is always going to give you 0, or it's going to give you the zero matrix. Okay? So those are the two special kind of matrices we just talked about here. Zero matrices, identity matrix. The identity matrix has to be square. The zero matrix, if it is square, you can multiply it times anything of that size. Now, if it's a rectangle, it can also be called the zero matrix, but it's not as used as often because you can't multiply a rectangular zero matrix times another matrix and get the same size of matrix. Okay, so most of the time we're going to be working with zero matrices that are square, but zero matrices can be other shapes too. Okay. How do you refer to a specific element of a matrix? So let's say that you don't know the values of a matrix, but you're talking about a matrix called matrix capital A. So here we are going to refer to each of the elements in the matrix with what we call index numbers. And so here you can see that I wrote down numbers 1, 1, 1, 2, 2, 1, 2, 2 to refer to the position of the matrix element within the matrix. Okay, so obviously the first box refers to the row that the element is in, and the second box refers to the column that the element is in. Okay, so sometimes if you have like really big row and column numbers like 13, 14, 15, something that's 2 digits, then you can't just write 1, 1. You're going to write 1, comma 1. Okay. Another difference is instead of small a, maybe sometimes they'll use big A to refer to the matrix element. Okay. So there might be this kind of notation. But I think that pretty much covers all the cases. Okay, so you might have commas in between these numbers, but you might not. Okay, so if I want to say, okay, what is the element in the first row and the second column, which would be that one, I would refer to it as A12 or capital A12 or capital A1, 2 or small a1, 2, something like that. Okay, so basically that says the element in the first row and the second column. First row, second column. Okay. Matrix size. When you add and subtract matrices, as you probably know already from your practice, you cannot add and subtract matrices that are not the exact same size. Okay, so think back to our investigation where you made your graphics GIF. When you made your GIF, you had 2 matrices that were the exact same size, and you made 2 images that were different, okay, of different different faces or a different a different word or whatever. And the thing that was common between the two is that the size of the two matrices was the same, right? So the width of each one was 20, and the height of each one was 14, okay? They were the exact same size, and because of that, we could add the corresponding elements in the matrices in order to get the combination picture which formed our morph GIF, right? We could superimpose the two pictures on top of each other because we started out with two separate matrices that had the exact same size, okay? So when you would add and subtract matrices, they must be the same size. And for example, they must have the same number of rows and the same number of columns. You can't like turn it on its side or anything. So I can't have a 20 by 14 matrix and a 14 by 20 matrix because one of them is sideways. So you cannot add and subtract even if the rows and columns are reversed. Both of them need to be 20 by 14, for example. Okay? What about scalar multiplication? Scalar multiplication was like the operation we did in the investigation where we had an image, right? And the image we multiplied times the number between 0 and 10, which was our scalar value, and then that made the whole image lighter or darker. So when you do scalar multiplication, it doesn't matter what size of matrix you're using. You may do scalar multiplication with any matrix, okay? But what happens is when you do scalar multiplication, what you get out is a matrix of the exact same size you started with. So if we had a 20 by 14 matrix to start out with, then our result after scalar multiplication might have all different numbers, but the size of the matrix continues to be, I'm sorry, I said 20 by 14. It's 14 by 20, right? Rows, columns. So 14 by, if you start with a 14 by 20 matrix, you end up also with a 14 by 20 matrix if you do scalar multiplication. Scalar multiplication does not change the size of the matrix. It keeps it exactly the same. Let's talk about matrix multiplication. Matrix multiplication, the sizes that you have of the two matrices that you're going to multiply together is not as easy to understand as the other matrices. I think the easiest way to understand is if you write out the matrix size in the row times column form. Like, for example, this one would be 3 times 2, and this blue one here would be 2 times 3. When you multiply two matrices together, the two middle numbers here have to match, okay? And then once those match, then you can figure out what the size of the new matrix is going to be after the multiplication by looking at the two outer numbers. So the size of the new matrix is going to be 3 by 3, okay? So once you figure out that those two matrices can be multiplied together in the order that you put them, it helps to rearrange them in the following form. So we'll put this here. Let's see. Okay, and then we're going to put the answer matrix here in between the two. Okay, and then when we multiply these two together, basically we're going to get a 3 by 3 matrix, as we can see from this picture, and the rows and columns we're going to multiply together are kind of like this. So to get this pink number, we're going to multiply the pink row times the pink column. And for example, to find this gray number here, we need to multiply this gray, or this gray row times the gray column. So we'll do these two examples to just show what you get. So if I multiply the row 1, 2 with the column 1, 4, I'm going to get 1 times 1 plus 2 times 4, which is 1 plus 8, which is a 9. Okay? And then when I multiply the gray row times the gray column, I'm multiplying 5 times 2 and adding it to 5 times 6. So that would be 10 plus 30, which would be 40. Okay? So I've just found two of the elements in the new matrix, and I can, by completing this, confirm that the size of the matrix that I'm going to end up with is a 3 by 3 matrix. Okay? One last thing is that if I completely reverse the order of the multiplication and I multiply with the blue matrix first and the red matrix second, you can see that I can still multiply them together, because instead of being a 3 by 2 times a 2 by 3, it's going to be a 3 by 2 times a 2 by 3, which is also okay, right? The middle two numbers are 3s. but it's going to be a different shape in the answer, because instead the answer is going to be a 2 by 2 matrix, right? So when you do matrix multiplication, you get very different answers and sizes when you reverse the order of the matrices. And in some case, when you reverse the order of the matrices, you can't do the multiplication, right? Because, like, for example, if I do a 3 by 1 matrix times a 1 by 2 matrix, that works, right? Because the middle two numbers are 1. But if I reverse the order and I try to do a 1 by 2 matrix times a 3 by 1 matrix, it no longer works, right? The middle numbers don't match anymore. So some matrices you can only multiply together in a certain order and not in the other order.